did a lot of changes to our batteries library. First thing I want to talk about is aging. Why do we need aging? We want to calculate and predict the long-term changes of the battery. Due to aging, we have a loss of performance in battery. We have a loss of battery performance due to usage, which is called cycle aging, and due to internal chemical reactions, which is called calendar aging. And this leads to a decreased capacity of the battery and an increase of the internal serial resistance of the battery. I would like to demonstrate this in a small example model, which is this one. This model is a battery-driven electrical vehicle. This is the battery, and we have a driving cycle which controls the vehicle. The driver drives the car 2 times a day for some kilometers, and our little charger model charges the battery overnight. And when it comes to aging, we go into this stack model, into the parameters. Here we have this new parameter set for aging. We can select between no aging, of course, or separate cycle or calendar aging. And in this model, we have both calendar and cycle aging. Everything comes with a certain set of parameters. For this calendar aging, we use the so-called Arrhenius equation, and the cycle aging is based on a curve which defines how fast the battery decreases. And then we have factors which change the capacity and which change the internal resistance depending on the number of cycles. Here you see our test model. It runs for 1 year because aging is a long-term. Here we have frozen result curves for no aging. This means capacity stays constant. And here is different types of aging. The red one is this combined cycle and calendar aging. Very nice feature, I think. I close the model. Next feature is dynamic cells. Dynamic cell models consider the short-term effects which occur when we have fast changes of the current through the battery. In a dynamic cell, the battery voltage reacts in a delayed way. This is implemented by additional, I open the parameter dialog of our cell model, and the dynamics is implemented by additional RC circuits. We can have up to 4 of these additional circuits, and the resistance and the additional capacitance are defined by lookup tables for different temperatures. Let's run this model. This model is a so-called HPPC, which is standardized hybrid pulse power characterization tests. It consists of it goes for over 24 hours, and the battery is discharged and charged using a certain regime. And we see here the green curve is a static cell, and in the red curve, which represents the behavior of the dynamic cell, we see the delayed response of the voltage of the battery. We did some other changes too, some other improvements compared to the old library. We now use SimulationX lookup tables instead of these lookup tables we had in the former library, which come from the Modelica standard library. Now we have our nice graphical user interface for all lookup tables. And we optimize the internal modeling of the batteries, which leads to a much higher performance for large detailed stack models. I have here a comparison of a sample model with a detailed stack which contains of 142 times 4 cells, which are closely to, I think, 600 cells. We achieved an improvement of the global symbolic analysis by factor 6. If we use a solver with compilation, we also improved the compilation time by factor 6. We reduced the number of state variables by 3 for certain parameterizations, which everything leads to a much gain in computation speed by factor 20.